Welcome back everybody to another GLSL tutorial, and in this video I want to cover a few things. First of all, define the version number and then cover the basic types which you can use in shaders, and also I want to show you how you can send data from your main program to the shaders and how you can send data between the shaders. So let's get started. First of all, define the version number. So you can use the version directive right here to define a version number, and this is waiting for the integer representation of the version number. Like if you want to use 1.2 version 1.2, you don't write it as a floating point number, but you write it as 120, meaning that you want to use 1.2 version right there. If you want to use 1.3 version, then just write 3 in here, or 1.4 version, write 4 in here, so on. So that is as simple. If you don't write this version directive right here, that pretty much mean that you are using some basic version, I don't know, probably 1.0 or 1.1. I have version 1.3, which is for OpenGL 3.0, which I have on this machine. But I will not show you the version 1.3 because some things like the GL model view matrix and GL vertex and GL position, basically every built-in variable become depraved. It's waiting for you to manually set it, the GL, so the matrix you should pass it as a uniform variable, which I'm going to cover later on in this tutorial. And it's waiting for you, the new OpenGL from version 3.1, to create your own matrix stack, create your own function for manipulating the matrix, and so on. So it waits for a lot of things. Then this GL vertex become depraved as well. It's waiting for you to manually pass the vertex position as attribute data using vertex buffer objects in version 3.1. And the GL position also become kind of depraved, and it's waiting for you to manually create this varying variable, and I cover all of these 3 times of variable in this tutorial. Okay, so I will show you actually I can show you that if I try to run the program at this moment with version 1.3, it indeed gives an error. So as you can see, it gives the error that GL model view projection matrix is depraved after version 1.2, and similarly the GL vertex is depraved as well. So that's why I will not cover the 1.3 version, although maybe later on I will show you how you can create your own matrices and stuff. But for now, let's cover the 1.2 version. So write version 120, so meaning you use the 1.2 version of the GLSL. By the way, the GLSL numbering will go from 0, so start off as 1.0, 1.1, 1.2, so on until 1.7, if I remember correctly, and after that it suddenly just jumped to 3.2 or somewhere at that range. So first of all, the GLSL version number is pretty much completely independent from the OpenGL version. For example, 1.3 is for OpenGL 3.0, and then 1.4 is for OpenGL 3.1, so completely independent. But later on, for example, OpenGL 4.2 uses the GLSL version 4.2. It doesn't really matter at the moment, but I just thought I might say that. Okay, and actually I will copy this version definition to the fragment shader as well. Right, so let me create a few variables which define the basic types. So there is the most common type is the floating point number, call it f, and just set it equal to something. By the way, the definition and the declaration of the variable is pretty much the same as in C++, similarly with the scopes as well, so it's only visible in this scope which this variable is defined. One important thing is that you shouldn't use explicit type conversion or implicit type conversion. Actually, you shouldn't use type conversion at all, because that will give an error or a warning. It pretty much depends what kind of data I get. But in version 1.2, although I have tried it in a moment earlier, and it actually doesn't give an error if I write 10, for example, instead of 10.0. But let's see if it does. No, it does not. It's weird. Anyway, so you shouldn't use type conversion. If you want to convert type, you should use the constructor of the given type. Every type has a constructor, so just write float 10, and this will convert it to a floating point number. So if you run it, it doesn't give an error now either. But if you use an earlier version, like you don't write this version 1.2 here, if you just write 10 as the assigned value, then it will give a warning, as you can see, implicit cast from integer to float. And you can't use the casting like float right there, it's probably give an error. You should use constructor in order to change that. Okay, let me write back this version number right here. The next type is the integer. This is the most used type. By the way, I don't really use integer, might be just loop variable or something, but in calculations not really. So this is integer I equal 1, for example. This is the integer. It's pretty simple. And if you use version 1.3, there is another type uint, which is the unsigned integer. Although in version 1.2 this unsigned integer does not exist yet. Okay, and the third basic type is the boolean. So it's a bool b, and this is equal to true or false as well. Okay, these are the base types. So now if I try, oops, not that one, this one. As you can see, just compiles fine, but because we don't use this variable for anything, this is pretty much just like tried out if it does compile without errors. Okay, but there are some complex data types which created from get more of this value. For example, get 3 floating point value and you have a 3-dimensional vector. To create a vector, which is an often used type in GLSL, you either use vector 2 for 2-dimensional vector, vector 3 for 3-dimensional vector, or vector 4 for 4-dimensional vectors. Like this GL vertex, this is a 4-dimensional vector. And you can just create this vector, like similarly use this as a type, so vector 3 vector, and just use the constructor to create a vector, like make it like this. So this vector 3 waiting for obviously 3 floating point numbers, and this 3 floating point numbers is converted to a vector 3, and this will be equal to the vector. That's a pretty usual way to assign values. Similarly, if you have a vector 2 object and vec2, actually we should call it something vector 2, then you can use the vector 2 constructor, and it's just waiting for obviously 2 numbers. For example, vertex coordinates in a 2-dimensional vector should in a 2-dimensional texture, the texture coordinate should be a 2-dimensional vector. Right, and you have the 4-dimensional vector which contains a W coordinate, and we don't really use manually that W coordinate. This is a perspective division, but building types like the GL vertex will use it. Alright, these were the vectors, and by the way, you can create other types of vector, not just vectors with floating point numbers, although in practice you usually use floating point numbers. But for example, to create an integer vector, you use the IVEC instead of vector, like that. And I really hope so that this is work, because I'm not used to use, not really using integer vector, so call it vector 3. And just try to run it to see if we get any. No, we don't get errors or warnings, so everything is okay. So this is the integer type of vector, and there is a boolean type of vector which is completely useless. Right, and now let's see the types which created from vectors. This is the matrix type. So matrix, this is the name, and then the dimension. So matrix 2 is a 2 by 2 matrix, matrix 3 is a 3 by 3 matrix, and matrix 4 is a 4 by 4 matrix. For example, the GL model view projection matrix is a MET4, so 4-dimensional vector, so 4 by 4 vector. You can actually create types like 2 by 3 vector, although these are completely useless. I never use them anywhere, because usually you want to create a matrix 3-dimensional or 4-dimensional. Other matrix types are useless. So for example, create a 3-dimensional vector, and I just call it matrix. Matrix, 3-dimensional matrix, 3 by 3 matrix, that's what I wanted to say. And to assign values, you can use matrix 0, which is the 0th column of a matrix. By the way, in C++ you use a matrix like this usually, so whenever you create a 3-dimensional or 2-dimensional array, you have values like this. So it's this is the 0th row, and 1, 2, 3 column, and so on. So these are how you indexing the elements basically. But in OpenGL you pretty much use 1, 2, 3, and then 3, 5, 6, and here 8, 9, like that. So as you can see, this is completely, it's basically rotated. This is something called transpose matrix. Although for now you don't really have to care about what kind of matrix you use, is transpose or C-type matrices, or column major and row major matrices if you would like. But later on it may be important. But for now, just let's stick with filling up this vector. So the first column of this vector you can create by a vector 4 object, and you can place it like 1.0, those 2.0 and 3.0, like that, and this filled up the first column. Similarly, you just pass 1 for the second column and 3 for the 2 for the last column. That's how you can fill up matrices, and actually you can use array subscription like a multidimensional array. So you can write like mat21, which is the second column the third column and second row, if I say it well. Yeah, I think I do. Anyway, these were the matrices which you can use, and pretty much that should be enough for now. Later on we will cover type like sampler, which is basically a texture and so on, but for now this should be sufficient. Let's go to the third actually, this is the third subject of this video, and how you can give data from the OpenGL program which you have wrote here to the shaders. The one type of data is the uniform data, so just write the uniform modifier right here before the type. It should be global, and then the type, which is, for example, let's make it a vector-free object, which is the free floating point number, and the last is the name. So I don't know, call it what should we call it? Color, and not really matter. So this is how you can define a uniform variable. You can use uniform variable both in the vertex shader, both in the fragment shader. And one important thing about uniform data, that it will not change between vertexes. Okay, so right here in the display function, let's actually fill up this uniform variable. To fill up a uniform variable, you use the GLUniform function, which is, and after that, you know, the typical OpenGL, basically these two letters, and what kind of data do you want to fill up. Now we have free floating point number, because this is a vector-free object. If you don't write I here or B, then this is a floating point number. So we want to use free F, because we pass free floating point number. The first parameter of this function is actually the index of this uniform variable, and you can get the index or the location of this uniform variable with a function glGetUniform location. This is the name of the function, and this function waits two parameters. One, the program which you search for the uniform variable. We have a variable program right here. This is the program which we have used to which we are currently using, and the second parameter is the name of the uniform variable as a character literal. So in this case, this has the name color. Right, and then the second parameter of the GLUniform, the outer function, is of course the free floating point number. It doesn't have any other parameter. So let me just create a 0.0, 0.0, 1.0. This is a blue color actually. By the way, you can store the result of the glGetUniform location, because this will not change between frames. It will only change if the linking of the program would be called again for some reason. So you can pretty much use it as a global variable or something, so you don't have to always call this function to get the location of this uniform variable. What else should I mention right here? Yes, I already mentioned that it shouldn't change between vertices, so you shouldn't put this GLUniform free F and change it between every vertex. I think we are pretty much ready to try it out. Of course, let's write something so we can see the result. So I have this color variable right here. This is a vector-free object. So in order to convert a vector-free object, of course, that's what I forget about types, the conversations and so on. You have to use the vector-free right here, and in the vector-for constructor, not the vector-free, the color right here, I wanted to say. The color right here, which is free floating point number, and then the final floating point number. So that's what creates the vector-for object. So before I go into that, let me actually explain this one. So if you want to do type conversion, because you often want to use type conversion, for example, you want to create a vector-for object, and I don't know, just call it vec. Then you call the vector-for constructor, and it's waiting for a few parameters. It's actually waiting for 4 floating point number, but actually it doesn't matter what form. So for example, you can pass in manually, like I did in the original. Right. So now we just pass 4 floating point number, but actually you can make a free vector-free object. So color, for example, the vector-free object in this case, and then a third floating point number. So this is 3 floating point number plus 1 floating point number, and that is 4 floating point number. If you have a vector2 object, like vector2 v2 something, then you can pass this vector2 object and 2 floating point number. So basically the idea is that the sum of the numbers should be equal to the constructor weight. So the constructor waiting for floating point number, you pass for floating point number, doesn't matter how you pass it, so what form you use. Vector 2 object and 2 floating point number, vector 3 and 1 floating point number, or a vector 4 and 0 floating point number, or 4 floating point number. Any combination works actually. So let me just delete this now that I have explained. Oh, and one more thing, you can get each component of the vector by either using array subscription like this, so it will give a floating point number, but a more common way is that similar than we do with C++ structure, use the dot x, for example, to get the x coordinate, y to get the y coordinate, z to get the z coordinate. By the way, there are no pointers or references in shaders, I just wanted to mention that. Okay, but actually the surprising thing that you can get the xy component. This is getting the x component and the y component, and it will result a vector 2 object. So vector 2 v2, and this is equal to the color xy, so we get the x and the y components from the vector. You can actually get the xx component from the vector, which is 2 times the x component. You can get the yy components, 2 times the y components. You can get the xz or zx, or any combination you can imagine. Alternatively, if you're working with colors, this same vector has an r, g and b component as well, so you can get rb or rg or rr and so on. Or if you are working with texture coordinate, there is an strq, maybe, I don't know, I don't use the last coordinate never in a texture coordinate, but this is basically how you can work with texture coordinate, by using the str. It doesn't really matter, you can use it, so use whatever. So the s is equal to the x and it is equal to the r, so this always get the same component. But you can, for example, use xs because s is for textures and x for coordinates. So you have to use this the same, so either use x, y, z, w, or gba, which is, or strq. Don't use the combination of this, right? And as I said, it gives back the same data. It's basically just so you can better understand the program later on whenever you're going through. Okay, so now that I have gone over that, let's try to compile the program. It should be here somewhere, and let's try to run it. Okay, and if everything goes correctly, and yes it is, then we get a blue triangle. How is that possible? So first of all, in the OpenGL, we use the GL get uniform location to basically get the location of this color variable. Then I set the color of this variable to blue, 0R, 0G, and maximum blue. And then in here in the fragment color, I just set the color as the fragment color, so the current pixel color equal to that color, which is blue. And this 1.0 is just for the alpha, because the alpha testing and alpha blending is not in the shaders, it's still fixed. Okay, that was it. So let's try the varying variable. And actually, before I do the varying variable, no, let's make the varying variable first. To create a varying variable, you use the modifier varying, and the type, of course, which, well, let's make it a vector-free object, a vector-free, and then the name of this. So I don't know, make it color2, whatever. Okay, and I just copy this to the fragment shader. It is important that both the fragment shader and the vertex shader have the same name. So what the varying variable is basically a variable type which gives data from the vertex shader to the fragment shader. So whatever you write here in this color2 variable will be visible in the fragment shader in the color2 variable. And an important thing about varying variable is that they interpolate between values. So for example, if one vertex gets the value 0 and the next vertex gets the value 5, and there are 5 pixels between the two, then it will be 0, 1, 2, 3, 4, 5. That's what the color variable, whenever you read in the fragment shader, will contain. So basically it does the interpolation for you automatically from in the vertex shader. So if you have 2 different values in 2 different vertex, then it will slowly one value go to the other value in the fragment shader. That's the basic idea behind it. So let's try it out immediately. So make the color2 equals to a new vector3, and this color should be, let's make it green for now. So we will see the result. And in the fragment shader, I will change this color to color2. So if everything goes correctly, the color2 will be set to green in the vertex shader. In the fragment shader, this color2 will be interpolated, although because every single vertex has the same color, which is this green, it doesn't really matter the interpolation for now. And then I set this triangle to the color green. So if I run the program, it should give a green triangle, and indeed this is a green triangle. Now the last type of data is something called attribute data. So let me create another variable for that. It starts with the attribute qualifier, attribute, and then the type again. Let's make it a vector4, and then the name. So I don't know, what should we call it? Call it ATR, like attribute, whatever. Okay, and actually this attribute variable is similar to the uniform variable. You set the attribute variable in the main program, but the main difference is that attribute variable can be set in every frame. By the way, this varying variable in version 1.3 was renamed out in the vertex shader, and in the fragment shader it were renamed in. So this type, the varying type, it doesn't really matter, but you may see that later on if you are working with other version. And this attribute variable in the vertex shader was renamed in the vertex shader. Right, that's about it, the changes. And so basically the input of any shader state is named in, and the output from any shader state named out in later version. For now we can use attribute varying and uniform variable. Uniform variable was not renamed, by the way. Okay, so we have an attribute input variable, and actually let's change this attribute right here to the attribute. Actually we don't need this vector3 right now. So what I'm going to try to do is set the attribute variable in the main program, give the attribute variable to the vertex shader, and with the varying variable give the result of the interpolation here as this varying variable. So let's try to make it first. Let's make an index. So index, this is an integer. GL get attrib location. This is how you can get an attribute location. It's basically the same function as GL get uniform location, and it's similarly waiting for the program and the name, which is ATR in my case. Then you can set the attribute by using the GL vertex attrib function. So let's set a different color for every single vertex. So GL vertex attrib. So GL vertex attrib. This is the name of the function, and similarly it's waiting for the data, which for example free f for free floating point numbers, and it's waiting for the index as the first parameter, index, and then the color. So make this first one to red. Okay, and let me copy this to the second, make it green, and copy to the third and make it blue. So if everything goes correctly, this vertex attrib data will go to the vertex shader. In the vertex shader I will give this to this varying variable right here, and the varying variable will interpolate this value between the different vertices, and in the fragment shader I will set the interpolated value to the current color. So let's try to compile it and see what's going to happen. And indeed it worked. As you can see, we have an interpolated triangle. I set the color of each vertex with the call, so GL so this call GL vertex attrib, and then in the vertex shader I set it to a varying variable, and the varying variable interpolated for us and make this final color of each fragment. That is how you can make it. By the way, after OpenGL 3.1, the only way you can pass data to the vertex shader and the fragment shader and anywhere is basically just the uniform variables and attribute variable. So for example, you don't anymore use the GL vertex, GL color, GL normal and calls like that, but everything you pass in as a attribute variable to the shaders, and in the shaders you work out the final stuff. Basically, I will maybe talk about this subject later on. So for now I will just stick with this GL vertex and GL color and so on calls, but later on similar way you can set the position with as attributes. Right, and I'm pretty sure this should conclude this tutorial. Thank you for watching and have a great